What happens if you run into a hard math problem? Oh my goodness, I did an equilibrium problem and it turned into a quadratic. What can I do? Well, there's several options if you find yourself in this situation. Here's an example. We're not going to go into how you would get to this situation. We're going to assume in this lesson that you kind of already know how to set up an ICE problem or something like that. And so what happens when you get to this step where you have this nasty thing that's going to devolve into a quadratic? Well, there are three options then that we can do. First option, obviously you can give up. Giving up is always an option. As long as you don't really care what you learn or where you go or what you're going to be, you can always give up and just not do the problem. But we're going to assume that that's not you because you're watching this video. Second thing you can do is you can try the 5% rule. So what's the 5% rule? It's going to take, most of this video is going to be talking about the 5% rule. It's what we use a lot of the time. Fortunately, it's really easy, but explaining it takes a little while. So what we're going to do with the 5% rule is you got your thing set up, and we're going to assume that x is some reaction amount, and we're going to assume that the reaction amount is very, very small. Like the reaction didn't go forward very much. So x is tiny. And by the way, this works better if your k value is small most of the time. So when you add or subtract a tiny number to other numbers, they don't change very much. That's the premise of the 5% rule. So we can ignore the change. You can ignore changes that are small mathematically. So what does that look like? So if we look at our original expression, what we're going to do is we're going to look for places where x has been added or subtracted in the formula. And so the first thing that we see, well, down here in the denominator, minus 2x, that's a case of x being subtracted, so that is a place we need to look at. Where else? If we look up there at the top, in the numerator, we have 0.00024 plus x, so x is being added there. And then the third thing we see is we see an x out in front. But notice, it is not being added or subtracted. It is being multiplied. If you multiply tiny numbers, that changes the answer quite a bit. Adding like 0.00001 to something isn't going to change the value very much, but multiplying 0.00001 by something is going to change your value a lot. So we are not going to ignore that x. So that is not a candidate. We're going to leave that x alone. So whoa, why isn't that twice? So let's go to the first one, the 2x. That's what it's going to look like if you ignore it. See, there's 0.058 minus 2x, and now we're just going to pretend we're not going to subtract the 2x, because 2x we're guessing is a tiny number. It's not going to change the 0.058 very much. And by the way, you might say, well, how do you know that x is small? Well, we'll get to that in a little bit. For now, we're just going to try our best to avoid a quadratic by doing this. So let's look for the other place. What's this top place going to look like whenever we get rid of the plus x? Well, it's just going to look like that. We're going to ignore it. The minus 2x on the bottom goes away. The plus x on the bottom goes away. But that multiplied by x there in the numerator stays because that's not being added or subtracted. So now we have a manageable equation. We can solve this in just a couple of steps by multiplying and dividing. We don't need to get out a calculator. Well, we probably do need a calculator, but nothing too terribly complicated here. We can go ahead and solve that. Why is that in there again? What? I duplicated some things. Oh well, I'm not going back. So if we solve that, I'm not going to show you how to solve that. We're going to assume you guys know how to solve equations like that for x, and we're going to, x is 7.0, well, what? 6.70 times 10 to the negative 12th there. So that is our x value. That is, we basically solved the equation, but is it right? That's what we want to know. Is it right? We made some assumptions there. So what we got to do now is we got to check our logic. So go back to the original equation the way we had it before, and now that we know what x is, we can just kind of plug x in there. So x is 6.70 times 10 to the negative 12th, and so that first term at the top, we had 0.00024 plus x. Well, now that we know that x is that number, we can actually add it in there and see what we should get. So if you add that, here's what you get. You get 0.00024 becomes 0.0002400000067. That's not a very different number there. That's pretty much the same number. You got to go out like 7 digits to find any difference. So I would say that ignoring that change is pretty much legitimate. That didn't change the number very much. But what about this other one? We got to be careful because this time the change isn't x, it's 2x. So 0.058 minus 2x, 6.7 times 10 to the -12th, and that equals 0.057999999. So 0.058, is that a very different number than 0.0579999? No. Again, you would have to have like, you're going to have like 7, 8 sig figs in order to be able to tell a difference. And we're usually going to round answers to like 3 or 4 sig figs. So we are pretty confident that that is allowable. So in our example, it was pretty obvious. We got such a tiny x, partly because I used such a small k value at the top here. That's a very, very small k value. So we got a really small x. So what if it's not as obvious? How much change is allowed? How much before we say it's a significant enough change that we've got to include it? The 5% rule. This is what we're going to do. We're going to look at the 5% rule. Now you know why it's called that. So what we're going to do is figure out whether if ignoring x changes that term by less than 5%, you're okay in most settings. Now obviously what you're trying to do, if you're doing research of some sort, it might matter. But for an average chemistry classroom, 5% change is going to be allowable if it's 5% or under. What does that mean? So let's verify that our test was okay. Here's the general idea. The added or subtracted term divided by the original number that it would have been added or subtracted from times 100 needs to be less than 5%. So our x value that we calculated was 6.7 times 10 to the -12th. So 2x is that, 1.34 times 10 to the -11th. And that is going to be our added or subtracted term. The original number was 0.058. So we're going to divide by that and then multiply it by 100. And that gives us a number that is certainly less than 5%. I mean, we could have had a 4.7 there and it would have been allowable, but this number is 10 million, 100 million, I'm not counting zeros right now, times smaller than that. So we are okay. We are good to go. But what if my term is more than 5%? What if we did all that, we ignored the x's, and we found that we got an x value that was more than 5% of what we should have subtracted or added it to? So what do we do then? Well, we're kind of back to square one. Our options we could still give up. Giving up is still an option. 5% rule is no longer an option anymore because we found that our problem had a change of more than 5%. So that brings us to the third option, which is to do math. And I know that this is hard and we don't like to do math. So I guess by doing math, we can always let someone else do our math for us. That is an option. So how can we do that? Well, there's lots of places that'll do math for you. The one that I usually use and recommend, it's quite nice, is Wolfram Alpha. So what we're going to do now is we're going to go to Wolfram Alpha and we're going to solve this equation. It's going to look something like this. So I'm going to take that expression that I had a little bit ago, 4.78 times 10 caret -13. That's how you're going to type into a box that you're using an exponential. And that equaled, this is just the original equation I had, x times 0.00024 plus x divided by parenthesis 0.058 minus 2x quantity squared. And we're going to hit enter. And it's going to do all of the thinking for us. And it's going to spit out all sorts of things. But what we really are interested in is the solutions. Down here we get the solutions. Now here's the thing about a quadratic. It's always going to give you two solutions. You know which of these is right because we just did the problem. We had 6.7 times 10 to the negative 12th was our answer. Turns out that if we had solved it analytically, we would have gotten almost exactly the same answer. Well, how do we know that this is the answer and that that isn't the answer? Well, if we go back to the original, you'll notice that we have a positive number here and a negative number here. So if we go back to the original equation, the original, there we go. You see that x is a term here. So x is, the question is, can x be negative? And we didn't really work out an actual problem. This is just an example, but an actual problem, x means something. X is usually an amount of something made. Like you start with 0 and you make x. Well, if you start with 0, you cannot make negative amount of something. If you have no chemical in a container, you can't then all of a sudden have a negative amount of it. That's just not a thing. So negative values are almost always not allowed in a situation like this. There could be cases, depending on how you set it up, where a negative answer could work, but almost always you can throw out the negative answer. But what if they were both positive? If they were both positive answers, then you'd have to use the one that made sense. For example, in here, if we got a number that sometimes, let's look down here, if x is a positive number, there's certain positive numbers that are not going to be allowed here. Any number that when multiplied by 2 is more than 0.058, that would produce a negative amount on the denominator. So you basically can't end up with negative mass, and so generally it's kind of a case-by-case basis, but this is going to be our answer here. And generally the negative answer you can throw out, or an answer that produces a negative value when you plug it back into the original expression. We can throw those out as well. And so that's how you do math when it's hard.